Okay, so we're very pleased to welcome Andrew, and he's going to tell us what he's talking about.
Okay, it's very odd to hear you call me Andrew.
Oh.
Let me share my screen. Hopefully now. Can you see that? Sorry, I'm not.
Yes.
Yeah, good. Right, so this is a follow-up talk to one given by Tony Robbin back in February, where he was discussing quasicrystals, and I'll review the key aspects of that talk as we go through. So this is fairly self-contained. But during that talk, Tony sort of threw out a question that I felt I was able to help answer. And so this is the story of the work that has been going on through the course of this year between myself, Tony Robbin, for whom, if you're not familiar with Tony, Tony is an artist who has a long-standing involvement with mathematics, and I've included one of his pieces of art on this slide. And also George Francis from the University of Illinois at Urbana-Champaign. George is a long-term collaborator of Tony's, and I have taken this picture and a couple of others from some slides that George produced a little while ago. So we're going to be discussing the generation of n-dimensional quasicrystals, but as I say, this is fairly self-contained. The story of quasicrystals originates with Roger Penrose's non-periodic tiling of the plane back in the 1970s. Roger Penrose didn't really have any awareness that this was anything to do with quasicrystals. He was answering the question whether or not it was possible to come up with a set of shapes that can only tile the plane in a non-periodic way. Now, of course, tessellating the plane with parallelograms is a fairly straightforward thing. So in order to force a non-periodic tiling, what Penrose did was define certain matching rules, visualized here by these little nodules. And this forced these tiles only to permit a non-periodic tiling. As it happens, if you look at the area of these two tiles, they happen to be in the golden ratio. Well, not long after these tiles were discovered, Robert Amann discovered that if you decorated these two tiles with these straight lines shown here on the left-hand side, then you could manifest the matching rules by saying that tiles can only be arranged so that these lines align across tile boundaries. And if you do that, then you get the picture on the right-hand side. And this is really what reveals the non-periodic, or what became known as the aperiodic nature of this tiling. The matching rules sort of certainly do give what looks like a non-periodic tessellation of the plane, but these lines actually reveal order in the chaos of this non-periodic tiling. So as soon as you place one of these tiles down, each of the lines across the tile tells you that there is an infinite line of tiles stretching out in the appropriate direction. Fairly obviously, if you look at the right-hand side, you can see that we've got 5 different parallel sets of lines, and you can see some pentagons in there. So you can see that there are 5 sets of parallel lines. These sets are parallel to the edges of a regular pentagon. You'll notice that there are some long and short spacings between these lines, and the same thing occurs in all 5 directions. If you looked at the ratio of the long and the short spacing between the lines, you'd find they were in the golden ratio. And if you count the number of long and short spacings in any one of these 5 directions, you'll see that the number of long and the number of short spaced intervals are consecutive Fibonacci numbers. So the ratio of the long and the short spacings, again, is in the golden ratio. So these Amann lines reveal this global symmetry, this five-fold symmetry within a structure that is non-periodic. And this is really what came to be understood to be an aperiodic tessellation of the plane, and lay at the heart of what became the topic of quasicrystals. In the early 1980s, de Bruijn, who was the subject of Tony's talk, carried out an algebraic analysis of Penrose tiling. Actually, it was really an analysis of the tiling set within the complex plane. And de Bruijn's analysis focused around the use of what he referred to as a pentagrid, which was 5 sets of parallel lines represented here by different colors. These lines exist within the complex plane. And if we imagine for a second that the center of this star of vectors that I've drawn in the center of this slide is our origin, then the lines in the grids that make up the pentagrid are those lines of complex numbers for which, if you rotate by some multiple of 2 pi by 5 and apply a shift, the gamma j that you can see in the slide here, then you end up with a complex number whose real part is an integer. So you can imagine rotating these various grids around and ending up with something aligned to an integer in the real part. There were some restrictions placed upon the shift parameters, the gamma j, but we don't need to worry ourselves too much about that for this talk. The key thing is that the particular integer on which the real part of these grid lines falls serves to number the grids or number the lines within a grid. And that in turn gives us the ability to assign some ordinal index to every region in the complement of this pentagrid. So I've highlighted one particular region here in the complement of these 5 sets of lines. It lies between the red lines indexed -2 and -1. So we'll assign the ordinal index of -2 in the red grid. And then similarly, it lies between 0 and 1 in the green grid. It lies between 1 and 2 in the brown grid. And so we get these ordinal indices. And this is used by de Bruijn's analysis, as you'll see in a second. Grids in general, these pentagrids, can be characterized by the shift parameters, the gamma j. And they're characterized, broadly speaking, as being regular or singular. So this refers to the type of intersections. So you can see at the bottom here, I've labeled one intersection where just 2 grid lines intersect as regular, which is what you would sort of expect if you had sort of just 2 linearly independent intersections. I've also got a singular intersection, which involves 3 or more lines. And this is a notion that we'll meet again a bit later on. So this analysis using pentagrids was related to Penrose tiling because de Bruijn pointed out that a regular intersection between 2 grid lines can be used to determine a parallelogram. And it's a parallelogram generated by the corresponding normal vectors. So in this slide, we have a green and a red grid line intersecting. And I've drawn bottom right the corresponding ordinal indices. And as you cross one of the grid lines, then one of the ordinal indices will increase or decrease, depending on which way you're moving. And so the normal vectors for these 2 grid lines will define this parallelogram that I've drawn top right. And what de Bruijn showed was that the parallelograms corresponding to one of these pentagrids did indeed tessellate the plane and corresponded to a Penrose tiling. He went one stage further, actually. He pointed out that if you take any parallelogram tiling of the plane and you join the midpoints of opposite edges of the parallelogram, then those midpoints join up to form lines that are isotopic in the plane to a a pentagrid. He referred to these lines as the skeleton of a tiling, and he demonstrated that there was a duality between skeletons and Penrose tilings. So Penrose tilings, in a sense, provide a template for constructing a tessellation.
Andy, could you just say that one more time? There were too many words.
Okay, so this is a De Bruijn pointed out that if you take a parallelogram tiling of the plane, join the midpoints of opposite edges, then those lines that you get across a parallelogram join up, as you can see here, to form what look like grids. They're not quite parallel lines, but they are isotopic to a pentagrid. And so this skeleton defines a duality between the skeleton and the corresponding Penrose tiling. An interesting thing about the De Bruijn grid is that it is periodic. The spacing between the grid lines is regular, whereas the Amann decorations were irregular. We had long and short spacing. Now, the relation between the two is associated with another concept that came out of work done by Penrose and John Conway, and that was to realize that the Penrose tiling had some self-similar transformations in the form of inflation and deflation. What that means is that you can dissect the two Penrose tiles in such a way that when you dissect these tiles, you end up with a smaller, self-similar version of exactly the same pattern. Put another way, you can inflate. So if you divide up the Penrose tiles in the way shown in this slide, then as you put them together, these various patterns on the Penrose tiles define a larger version of what you started with. And it turns out, although it's not something we really need to focus on for this talk, but the difference between the regular spacing of De Bruijn's pentagrid and the irregular aperiodic spacing of the Amann decoration is related to this idea of deflation. So if you take a Penrose tiling, draw in the Amann decoration, then you take the deflation of that Penrose tiling, you will see that the deflated tiling and the Amann decoration are dual in this De Bruijn sense of skeletons and tessellations. So that's the link between the two. So all of these things are fairly tightly linked together, and they generated a huge amount of interest in these quasi-periodic or aperiodic tessellations of the plane. All of this was done in the 70s and early 80s. And it spawned a huge amount of interest within the physics community in particular to see if we could come up with a three-dimensional analog of this Penrose tilings. The reason being that it was seen by the physicists as an opportunity to create new materials with not a crystalline periodic structure, but some sort of aperiodic structure that had a certain global symmetry, much as we saw with the five-fold symmetry of the Penrose tiling, but with non-periodic characteristics as well. And the search for a three-dimensional analog focused on these properties, a finite set of, well, not parallelograms, but parallelepipeds in 3 dimensions, or so-called unit cells, with some simple set of matching rules, hopefully some simple inflation and deflation, with maybe some kind of decoration that revealed the periodic or quasi-periodic structure of a multi-grid in 3 dimensions. But really, these are sort of just extra characteristics that people are looking for around some kind of non-periodic tessellation of 3-dimensional space. 2 different mechanisms for generating 3-dimensional analogs of Penrose tilings emerged. Projection methods, which is what Tony was dwelling upon in his presentation back in February, and then a generalization of the pentagrid approach, which is referred to as the generalized dual method. So let's just review what Tony was talking about back in February. The projection method that Tony described, let's talk about the two-dimensional case to start with. If you remember that talk, or if you've watched the video, then you'll see that it is a mechanism for projecting the cubic lattice in 4 space onto two-dimensional space by projecting into 2 space those points of the cubic lattice that themselves could be projected onto a pentagonal target. And this is the main characteristic of these projection methods, that there is some kind of selection process. There is a target in some higher dimensional space, and those lattice points that project onto the target space are then projected into your tessellation space. So we went from R4 into R2 for a two-dimensional case, and Tony showed that if we took a rhombic triacontrahedron, then we could do the same thing by moving from the cubic lattice in 6 dimensions into 3 dimensions and create a 3-dimensional analog of the Penrose tiling. And Tony's main interest in doing much of this work is to understand the unit cells of the tessellation rather than the larger sort of aperiodic notion. And you'll see if you go back to Tony's talk that the unit cells of the 3-dimensional tessellation were sort of explored by projecting the coordinate axes from R6 down into these 6 vectors located around a regular dodecahedron shown bottom right, and then selecting the groups of 3 of these axes to reveal the unit cells that made up the tessellation of 3 space. And this is where the question came out, because Tony was then postulating that this projection technique would extend into 4 dimensions. And back in the 1980s, he started looking at what the unit cells might be in 4 dimensions, but didn't complete that task. Of course, computing power in the 1980s was very different to what it is today. So this is where I thought, well, I can help out with some coding of this geometry, which is where I got involved. Let's have a look at the other method, though, the generalization of the pentagrid approach of de Bruijn. De Bruijn's approach had 5 sets of lines parallel to the faces of a pentagon. Equally, you could say, well, he had 5 sets of lines parallel to a star of 5 vectors. Those 5 vectors would go through the faces of a regular pentagon. So if we generalize this approach, this was done for 2 and 3 dimensions in the 1980s, but this is what we've generalized now into 4 and generally into n dimensions. And so this is what you see here is the generalized method described to you in n dimensions. Interestingly enough, this is all we need to generate tessellations, but this is the description of it. So we start with a star of some number of vectors in n space. We're not going to be doing any projections. We're just in n space. So Rn here is the dimension of the space that we are wanting to tessellate. We're going to choose a set of n vectors that span that space, but we're not saying anything about the linear dependence of the vectors E1 up to E uppercase n. For each of these vectors, we're going to construct an infinite set of hyperplanes normal to that vector. We're going to call these a grid. I'm not saying anything at this stage about the spacing of these hyperplanes. They might be regular, they might be irregular, they may be periodic with long and short spacings. I really don't care at this stage. But I can create an infinite set of these hyperplanes, and then I can look at the complement, the regions that this multi-grid defines. The components of the complement are convex open sets in n space. And in the same way that we had in the case of 2 dimensions and the de Bruijn pentagrid, I can assign an ordinal index to each of the hyperplanes in each grid. So basically, starting from the origin, I'm going to choose one of these components as my origin. I've got these star vectors, so I head out in one direction along these star vectors. I'm going to encounter hyperplanes normal to this chosen direction of travel. And in that direction, I just start numbering my hyperplanes from 1. So what that means is that I can again assign a set of ordinal indices to each component of the complement of this multi-grid. So the component containing my origin is going to be indexed with all zeros. And as I cross each hyperplane in a grid, then the ordinal index associated with that direction of travel will increment or decrement, depending upon which way I go, by 1. And you'll see some examples of this as we go through. And then following the de Bruijn approach in 2 dimensions, we can then assign a set of points by constructing the linear combination of the vectors using these ordinal indices to each component. Now, this is tantamount to creating these parallelograms that we saw in the de Bruijn approach. We are going to be creating parallelotopes, and it is claimed here that, well, you really do get a tessellation if you do this in any dimension of space, regardless of the set of vectors you start with, provided that they span n-dimensional space, and interestingly enough, regardless of the spacing between the hyperplanes. What we will require, as you can see here, is that there is a minimum separation between any parallel hyperplanes in the multi-grid. Doesn't seem too much to ask. And for now, we will assume we'll use the same terms of regular and singular, so that in n space, a multi-grid or an intersection point is going to be considered to be regular if it is the intersection of exactly n hyperplanes. So you have n linearly independent hyperplanes intersecting in a unique point. And we'll talk about singular intersections a little later on. So let's go back to the 3-dimensional analog of Penrose tiling and look at this dodecahedron that Tony was showing us. And what do we see? We see a star of vectors centered at the origin of the dodecahedron. These vectors have been chosen so that they are normal to the faces of normal to adjacent faces of the dodecahedron. And we can create an infinite set of parallel planes in 3 space, normal to each of these vectors. And we would create a multi-grid in 3 space. So this is going to be a set of hyperplanes or a grid of hyperplanes. If you take a cross-section of a grid of hyperplanes in 3 space, you end up with a multi-grid in 2 dimensions. 2 dimensions is what I'm trying to allude to top right. But in 3 dimensions, if we take these normal hyperplanes and let's space them in an analogous manner to the Amann lines that we saw in 2 dimensions, we're going to have long and short spacings. And we're going to do that so that they are arranged with this sort of Fibonacci characteristics that we saw earlier on. If we look at the regular intersections of 3 planes, then now we can identify parallelepipeds, and they're generated by the 3 normal vectors corresponding to the 3 planes intersecting at that point. And it turns out, if you look at the different ways, so there are 20 different ways of choosing 3 of these normal vectors out of 6, and you get exactly the same unit cells that Tony was describing. There are 2 distinct cell shapes. You can see them on the right-hand side, and these tessellate 3-dimensional space And if you look at a larger picture of three-dimensional tessellated, then, well, this is what it looks like. Actually, if you look at this picture, then you'll notice quite quickly that they're not just parallelograms or parallelepipeds here. The red cells are actually rhombic triacontrahedra. The blue cells are rhombic icosahedra. The yellow cells are rhombic dodecahedra. And it's only the white cells that are actually parallelepipeds. Now, the reason for that is the profusion of singular intersections where we have more than 3 planes intersecting at a point. But I'll come back to that a bit later on, and you'll see how this all resolves. The point is that this generalized dual approach does indeed give us a way of tessellating 3 space. So what about 4 dimensions? Well, Tony posed the question, what should the target be in the select and project approach? And we're starting to look at unit cells from that perspective. I took the slightly different view and looked at it from the generalized dual method. If you look at what we're doing in 2 dimensions and 3 dimensions, then the unit cells in 3 dimensions we just saw were generated by normal vectors in a star corresponding to adjacent faces of a 3-dimensional dodecahedron. If you go back to 2 dimensions, you'll see that the 2 Penrose tiles can be generated by adjacent faces of a regular pentagon. Now, it's true that the tessellation of 2 space required all 5 directions around a pentagon, whereas the tessellation of 3 space required only 6 normal vectors amongst the 12 around the dodecahedron. But putting aside such things and just sort of carrying on blindly with this idea of using adjacent faces, then there was a natural extension into 4 dimensions using the 4-dimensional hyperdodecahedron, or the 120 cell that Tony was discussing in his presentation. So the 120 cell is the 4-dimensional analog of the dodecahedron. It's a beautiful geometric figure. It has 123 faces. These 123 faces are dodecahedra. Each of these 3 faces is adjacent to 12 other 3 faces. They meet at the common pentagon, the pentagonal face of the dodecahedron. And if we want to mimic what was done in 2 and 3 dimensions, we would need to identify the center point of adjacent 3 faces around a 120 cell. Well, the center points of the 3 faces form the vertices of the dual polytope to the 120 cell, which was also mentioned by Tony, a thing called a 600 cell, which is the 4-dimensional analog of an icosahedron. So it's relatively straightforward to identify the Cartesian coordinates of the center of 13 adjacent 3 faces around a 120 cell. And with modern computing power, it's quick and easy to evaluate the center points and look at adjacent faces of a 120 cell. And of the 13 adjacent faces, choose 4 of them in all 715 ways, and we can discard the degenerate cases, which have so we're using the 4-dimensional determinant, of course, to come up with a 4 volume. So there are 135 cases out of the 715 that are linearly independent. What we end up with, if we filter through the rest of the structures, is that we end up with 10 distinct unit cell shapes. These 10 distinct shapes fall into 4 groups. Those 4 groups are they're grouped with 2 shapes in the first group, 3 in the second, 4 in the third, 1 in the fourth. Each of the members of each group has the same 4 volume. The ratio between the 4 volumes of successive groups is the golden ratio. So it mimics exactly what we saw in 2 dimensions and 3 dimensions. It's just that we've got a lot more unit cells. Those unit cells have 5 distinct 3-face shapes. They come in 3 distinct 3 volumes with some easily identifiable ratios, the golden ratio and root 2. There are 3 distinct 2-face shapes and so on. I wasn't able to identify a nice description of the last irrational number. I did play around with it for a little while, but I couldn't come up with anything particularly interesting. Nevertheless, there are 10 distinct unit cells that we can generate. And here are 2 of them. Lockdown gives you plenty of time to draw nets and make little models. So this was all very encouraging. We had 10, which is a reasonable number of unit cells that seem to be distributed in terms of volume quite nicely. But do they tessellate? Does this method really give a tessellation of 3 space? The generalized method is placing vertices of the tessellation, claimed tessellation, by taking components of the complement of a multigrid, looking at the ordinal indices of each of those components and using those as coefficients to create a linear combination of the normal vectors. So you get what looks very much like a linear mapping between 2 different dimensional spaces. Now, the thing is that we need to make sure that these unit cells are really going to tessellate. They've got to line up at a particular vertex. They've got to be aligned upon faces. You can't have any, that this mapping would have to be injective. You can't have distant vertices actually mapping to the same point. This matrix that we can form out of the column vectors, produced by the star of vectors. So my E1 through to En are the star that's defining my multigrid. I can create this matrix M, but it'll certainly have a kernel. If you know that the thing tessellates, then it's quite easy to see that you can regard the domain of this mapping as a vector bundle of the kernel of this matrix over the tessellation. And if you know it's a tessellation, you can see that that tessellation is actually a section of that vector bundle. And you can go further, you can see that the grid spacing of the multigrid will determine exactly which section we're talking about, because the grid spacing will determine which lattice points in the domain correspond to components in the complement of the multigrid. But doing it the other way around is a lot more difficult. Trying to regard this linear mapping as a vector bundle of its kernel over its image, and then trying to show that a section of that vector bundle corresponded to a tessellation, that's a lot more complicated. So we don't focus too much on that, although it's very interesting. And you can see now from looking at from this perspective how the projection methods and the generalized dual methods are certainly linked. Nevertheless, it is possible to show that we do indeed have a tessellation, and it revolves around just showing that these points do meet up nicely at a vertex, at a face, and that we don't get any, we have injectivity between the vertices. I'll just give you an idea of how this works. The challenge is that in the Bruijn case, where we were working in the complex plane, it was a very concrete example. There were 5 grids. You knew exactly what direction they faced in because we were just looking at orientations of 2 pi by 5. We knew exactly, the spacings of the grids. In general, we don't here. We know that we've got some number of grids. We don't know how many. We don't know what the normal vectors look like and so on. So how can we sort of just come up with an argument that is essentially combinatorial and is not relying on anything too concrete? Well, first of all, we need to look at tessellation of a vertex. So if I look at a component of the complement of the multigrid. I have to draw you two-dimensional pictures to make it accessible, but these are topological n balls. Their boundary are n-1 spheres, piecewise linear n-1 spheres, and they contain vertices in in those boundaries. I'm assuming for the minute that everything is regular, so I'm only assuming that we're going to have n hyperplanes intersecting at a point, and we'll deal with the singular case later. So if we're talking about regular multigrids, then things intersect nicely, and each of the 6 vertices around my component that I've drawn here are going to correspond to a parallelotope in my n space. But what is being positioned by the generalized dual method are the regions of the complement. So rho is going to get mapped onto some point t, and the adjacent regions are going to be mapped to nearby points. What do I mean by nearby points? Well, if you cross one of the grid lines into an adjacent region, then the ordinal coordinates will change only in respect of that one grid whose hyperplane you have crossed. And therefore, the point to which the adjacent region will be mapped is going to differ from t by just one of these normal vectors. So what I've done here is I've drawn the normal vector for each of the n-1 faces of the boundary of this n-ball component rho. It's important to realize there's no metric association here. I'm looking at these regions that are adjacent to my chosen component rho. So the red region that you move into by crossing a green grid is going to have ordinal indices differing by 1 in the green direction. So it will be mapped to t prime, which is one green normal vector away from t. If I'd gone the other way, I'd be moving into the pink region, moving backwards into what I've labeled as t triple prime. If I cross the purple grid line into the adjacent region, I'm going to be moving by 1 vector in that direction. So I could take these normal vectors around the boundary of rho and create a star of them, as I've shown on the right-hand side, at the point to which rho is mapped. And then you can see quite easily that the points in the boundary of the component that is represented by rho correspond to parallelotopes generated by the corresponding normal vectors. And of course, I mean, in this picture, it looks like they all match up rather nicely and so on. Well, this is 2 dimensions. It's really easy. It's all nicely intuitive. To ensure that you come up with an argument that shows that you're not going to miss anything, you need to notice that the normal vectors back in the multigrid are in bijective correspondence to vertices of the dual polytope rho star to the 3-ball, to the piecewise linear sphere that is the boundary of rho. And then you can see that there's a bijective correspondence to the parallelotopes around t to the faces of the dual polytope rho star. And because you've got the entire boundary of rho star covering, it's a sphere again, then we can show that we've not missed anything and everything packs together neatly at a point. Showing things fit together neatly at faces is probably slightly easier. These are parallelotopes. So parallelotope faces come in pairs. The n-1 faces come in pairs. And they're generated by a selection of n-1 of the generating edges. So in the sort of classical picture of a tesseract, you get sort of the blue and the red, as I've shown here. If you look at it on the right-hand side, you can see that this point in the middle here is going to be generated. It's going to have 2 faces, and they're going to correspond to the intersection of the blue and the purple planes, and they're going to be either side of the green plane. And you can see that the blue and the purple plane intersect in a line, and this will always be the case if you take n-1 of these hyperplanes that would normally intersect around a point. If you take n-1 of them intersecting in a line, the intersection of the blue and the purple plane will intersect every parallel copy of the green. That line will intersect everything that's not parallel to it. And so you can look at adjacent ones and that you can see that they will have matching faces. So that sort of sits together quite neatly. The injectivity is probably the most complex thing to show. And it hinges upon an observation that if you take any two components of the complement of a multigrid, then you can join those two components by a straight line. I've given you two examples here, a red and a green, that only ever crosses one grid line at a time. You never, as you go along this line between these 2 points, you never go through an intersection point between two grid lines. You can prove that this is the case by considering, again, these piecewise linear n-1 spheres that bound the boundaries of the components of the complement. There's a finite number of components that the red and the green lines, these straight lines intersect. So their boundaries have a finite number of cells. And you can come up with an argument based on choosing intersection points of minimal dimensions and just nudging this line a little bit away. You need to bear in mind that this straight line, because the endpoints lie in the complement of the grid, then anything that these lines hit are only going to be intersecting in a point. You're never going to be intersecting anything more than a point because the endpoints, the line doesn't lie in one of the multigrid, one of the hyperplanes. So once you realize that you can join any two regions by a line that crosses only one grid plane at a time, it's relatively easy to see how you're never going to get two distinct components mapping to the same place. Because if I look on the top right, I've got two components, rho and rho prime. And I've got two points, x and x prime, in these two components that I can join with a line that crosses only one grid line at a time. I can look at a hyperplane normal to that line, h, and I can then trace my way along from x to x prime, and I'm only ever going to cross one grid line at a time. And if I look at the corresponding point t, so x is mapped to t by the GDM, that's the linear combination corresponding to the ordinal coordinates of x. And I look at a parallel hyperplane, h prime, which is parallel to h, but it contains t. Then, as I move along from x to x prime, I'm going to cross these various grid members one at a time. And each time I do that, I correspond to moving from t along a normal vector. And you can see, if you sort of go through it, you can see that each time you do this, you move further away from h prime. So we can show that t is, I haven't labeled it, it should be t prime, bottom right, I beg your pardon. T prime is distinct from t. We can do all of this, and we don't need to understand how many grid lines there are. We don't need to understand where they are, but we can show that the tessellation really is a tessellation, that this GDM method always produces a tessellation of n-dimensional space, provided we've got a non-zero minimum separation between planes. Although, of course, everything here has been regular. All of our points have intersected nicely. What about when I get multiple intersections? Well, Bruijn considered this back in his paper looking at two-dimensional space. And in his nice concrete example, he was able to show that you could just perturb the grid lines a little bit and resolve the singular intersections into sets of regular intersections. So if you look at the diagram top left, you can see that the vertical line has been moved slightly to the right of a pair of intersections. And I have labeled 6 regions around a cluster of 3 such intersection points, 1 through 6. And below, I have drawn the corresponding parallelograms to those 3 points. And so the 6 regions labeled 1 to 6 are mapped to the 6 vertices of a hexagon, which is then dissected into 3 parallelograms, and the 3 parallelograms correspond to the 3 regular points of intersection that you can see within the upper diagram. And then at the bottom on that left-hand side, there's the corresponding set of 3 parallelograms around the lower crossing. In the middle 3 diagrams show the same intersection point, but now the vertical line has been moved to the left. And we get a different dissection of the same underlying hexagons. But they're different because the line has moved to the left. And on the right-hand side, you can see the same process. And again, I've labeled this 1 through 10, so that here we have an intersection of 5 grid lines, and they've been moved apart in some manner. And now we end up with a decagon. And again, it has been dissected into parallelograms. Now, this was done by Bruijn in his nice sort of concrete example of his pentagrid with regular spacing and so on. But we can certainly take this approach. I showed you, or at least we can take this approach in the 2-dimensional case. I showed you a picture of a 3-dimensional tessellation with rhombic triacontrahedra, rhombic icosahedra, rhombic dodecahedra. When the tessellation of 3 space was done, rather than trying to do something like this and perturbing planes in 3 space, it was easier. Easier. What do I mean by easier? The analog of the Amann decorations was easier. The matching rules turned out to be easier by, rather than dissecting, just drawing a sphere around the singular intersection and looking at the whole rather than the inner dissection. So if you look on the right-hand side, my sort of 5-fold intersection point gave me a decagon that was dissected. Well, let's just think of it as a decagon. So if we do this in n-dimensional space, I take a singular intersection and I surround it by an n-1 sphere. And I look at the intersection of the n-1 sphere with the hyperplanes. Well, I get a set of n-2 spheres. I've drawn you a case of, I've got a 2-sphere here with 3 1-spheres, 3 planes intersecting it. And you can see that if you do this, the regions into which the n-1 sphere is divided are diametrically symmetrical. So there are always diametrically opposite points. And if you take a pair of diametrically opposite points in each of these regions, and you look at the convex hull of those points, you end up with a zonotope. You end up with a centrally symmetric figure. All I'm doing is describing to you, without reference to 5 lines or regular spacing or anything, the way in which you can describe the creation of the decagon in the pentagonal case. And this is exactly what happened in the 3-dimensional tessellation, and we ended up with the rhombic triacontrahedron, the rhombic icosahedron, the rhombic dodecahedron, and so on. However, although that works, and it worked for the physicists working on the 3-dimensional case, and it does produce nice, simple matching rules for zonotopes, you end up with these more complex unit cells. So you've got a range in general, you've got a range of parallelotopes, you've got a range of now zonotypes. And what are they? Well, it will depend upon the nature of the singular intersections, how many hyperplanes are intersecting, and so on. It makes extending a proof that you're going to get a tessellation to singular intersections much, much more difficult. But it turns out you don't actually need to worry too much about this, because focus on the fact that the multigrid is like a skeleton to the tessellation. It is a template for creating the tessellation. And so it turns out that you can resolve singular intersections locally. You don't need to worry about globally perturbing hyperplanes. We don't know, exactly what the nature of this star of vectors is. We don't know how many vectors we've got. We don't know what the plane spacing is. Trying to come up with an argument that tells you that somewhere off in infinity, we're not going to, so if we perturb a hyperplane a little bit, how do we know we're not going to create other singular intersections? But you don't need to worry about those things if you just consider a singular intersection locally. We can separate, we can isolate a singular intersection inside an n-ball, a small neighborhood, spherical neighborhood, because we've got the minimum separation of hyperplanes. If we do that, if we've got a singular intersection in a point, there must be a linearly independent set of those hyperplanes amongst everything that's intersecting. So we take one of that linear intersection set and we push it away from the point of intersection. That's what I'm showing in the middle picture at the top. So on the top left, I've got it's meant to be an n sphere or an n ball around a singular intersection in n space. And I can take one of my linearly independent set and push it away from the point of intersection, but leave it outside of this neighborhood, this local neighborhood. It'll be left unchanged on the boundary, just pushing it away inside. Because this is a linearly independent set, they intersect at a unique point. So within this neighborhood, if there's anything else, if I've got singular intersections, well, they can't involve the same number of hyperplanes that we had to start with. So we can repeat the process. And on the right-hand side, I'm showing that we repeat the process again. And we can do this as many times as we need to. And within the small neighborhood of my singular intersection, I can resolve the singularity so that I only end up with n hyperplanes intersecting at a point. Well, of course, they're not hyperplanes anymore, are they? I've just perturbed them. I've pushed them away. They are n-1 manifolds, but they're flat in the sense that they are isotopic to, or homeomorphic to an n-1 linear subspace that is the identity outside of this neighborhood. So because they are flat outside, these manifolds are flat outside the neighborhood, I can talk about them being normal to a normal vector. I can use the same ordinal index inside the neighborhood as I'm using outside the neighborhood. So I can continue to use the GDM template to assign parallelotopes to the intersection points of flat manifolds within a neighborhood. And if we do this, then we can extend the arguments around tessellation and injectivity to these regular neighborhoods, and we can extend our proof that the generalized dual method really does produce tessellations even in the presence of singular intersections. And if you look at the various choices that you have for which member of the linearly independent set to push away and the order in which you do these things, this corresponds, this set of choices corresponds to the different ways that you can dissect the zonotope that you would get if you considered the neighborhood as a whole. So, do we have a four-dimensional quasicrystal? Well, we know that if we take any reasonable star of vectors in n space, by reasonable I mean that span the whole of n space, that we're going to get a tessellation when we combine them with a multigrid. Well, the multigrid has to be sort of have this minimum separation characteristic. We can space our hyperplanes in the multigrid pretty much any way we like. We could do it in a quasi-periodic way using the Amann long and short. We can get five-fold symmetry. We will get a tessellation. Is it a quasicrystal? Well, we've got something that has unit cells with volume properties analogous to Penrose tiling. They come in groups and they're in the golden ratio. So from that perspective, choose your favorite definition of a quasicrystal, and the answer may be yes or maybe no. Is there an analogous Amann decoration in 4 dimensions? We don't know. Do we have self-similar inflation and deflation of unit cells? Don't know that either. My particular interest was that the unit cells that we created really do tessellate, and we've shown that to be the case. And so I think I'll leave the questions about Amann decorations and inflation and deflation to the crystallographers. So that comes to the end of our story. I've put some references here for the main set of papers, de Bruijn's papers, the quasicrystal in 2 and 3 dimensions, and the original part of the generalized dual method. I've put a reference of Tedesco's beautiful animation of the 120 cell. It's only about 5 or 10 minutes long. It's well worth watching. It's a thing of great beauty. If you have any interest in the details of what I've been talking about, drop me an email and I will send you my notes. But at that point, thank you very much for listening, and I will stop sharing.
Well, thank you very much. Very interesting. Are there any questions?
I have one.
Okay, go ahead, Dale.
Could you give me a definition of quasicrystal?
So the best definition, the best definition I can give you is of a tessellation of n space that is non-periodic and yet exhibits some global order and symmetry. If you think back to the Amann decoration of the Penrose tiling, you can see that there is some global fivefold symmetry because the decoration shows that there are parallel lines parallel to the faces of a pentagon. So there's order and symmetry. It looks the same if you rotate it by 2 pi by 5. There are periods there. There are long and short spacings.
Mm-hmm.
If you look at some definitions of a quasicrystal, then people would require that there are 2 or more periods associated with that tessellation whose ratio are an irrational number. My view is that the notion of a quasicrystal is somewhat subjective. And if you look at different papers, you will see slightly different definitions, but they all have those common features. It's a tessellation of n space. It's non-periodic, but it has some kind of global order, either in 1 or more periods that are irrational in their ratio, or there is some orientational symmetry at some large scale. The term was coined to reflect a crystalline structure that wasn't regular and ordinary. And Tony mentioned in his talk back in February that there were alloys of magnesium and aluminium that have been found to exhibit exactly this sort of structure. So there are physical substances that have these characteristics, but the term quasicrystal has become to sort of cover a more sort of, it's more of an umbrella term for these sort of tessellations.
Thank you.
If you have these hyperplanes and the separation varies, say, according to some irrational, what's the term? Non-related irrational numbers. I mean, do you get something which is non periodic?
Yeah, for sure. I mean, if you take a star of vectors that are the standard orthogonal Cartesian axes for n space, and you choose regularly spaced hyperplanes normal to those vectors, then regardless of how you space them, the tessellation you end up with is just the sort of a tessellation of n space in cubes. So yeah, this model will certainly generate things which are not aperiodic. The point is that regardless of what star of vectors you start with, regardless of the spacing between the planes, provided there is always a non-zero minimum spacing between parallel hyperplanes, you always get a tessellation, which is kind of interesting, because when you start thinking about that in relation to these linear mappings that you get from the matrix of the star vectors, it tells you quite a lot about the structure of that linear mapping.
So go ahead, Jack.
Turn on your mic, Jack.
You need to unmute yourself.
Is there some kind of orbifold associated to this tessellation, or these kinds?
Some kind of protocol.
Or orbifold,
Oh,
orbifold quotient.
I don't know. Maybe.
So I have two questions. When you were talking about the 120 cell, I'm currently in the habit of thinking about that as a subset of the 3-sphere. And so I got a bit confused about where the normal vectors are. Do I just take the ordinary coordinates of the 120 cell
Okay. So
as the icosahedral group?
yeah, so the normal vectors, so the origin is at the center of the 120 cell, and the normal vectors go from through the center of adjacent 3 faces on the 120 cell.
Ah, okay, okay,
And
thank you.
those center points correspond to adjacent vertices of a 600 cell, of course.
Right, right, okay.
Which is how you can figure out which ones are adjacent to each other, because of course they're joined by an edge on a 600 cell.
Right, right. So the other question is far more philosophical. Have you played with one-dimensional? Have you tried to drop the dimension down?
Well, Tony talked about this in February, and Bruijn actually did an analysis of that prior to his 1981 paper that I was referring to. So I haven't played around with that, but what you get is the sort of the long and short spacing with this sort of Fibonacci characteristic. And if you look, you count the number of long and short between 2 places, they're adjacent Fibonacci numbers and so on.
So the reason for asking is that I recall an article which says that solutions to the Riemann hypothesis correspond to some classification or something of one-dimensional quasicrystals or such a thing.
Well, it would be,
not that I understand that, but that's
well, it would be fascinating, and would certainly make you famous if you could prove that there was a solution to the Riemann hypothesis from quasicrystals. I think it would be a brave man who could do that. But who knows? Maybe that's the missing link.
I'd like to say something. I'm just amazed at how powerful this method was, and Andy's method of being able to sort through all possible combinations and see how they sort it out. We have the 10 bricks. We have them in 4 volumes. We have 5 cells, 5 distinct cells, only 3 kinds of faces. It's astounding that, you know, we really know everything about it, about the unit cells of the 4-dimensional quasicrystal. My problem going forward is I can't really visualize it, and I need more. I need many units of these of the 5 cells here, and I can show them.
Yeah, this is why we started building these things, Tony, isn't it?
Right. I don't know if you can see these. These are the 5 different cells from Andy's net. If I had hundreds of them and put them together, I could somehow get a better view of it. George Francis did computer visualizations, and that wasn't really a great help because they all look like hypercubes, skewed hypercubes, and to determine which of the distortion was the projection from 4 to 3 or 3 to 2, and which was intrinsically a different figure was very hard. So I'm still in a little bit of a quandary. The other thing I wanted to say is that once you have these unit cells, you don't really know where they are in the tessellation. And you need another mechanism like the dual method to place them in space. We know the limits of how they can fit together. Certain pieces can fit together because they're the quasicrystals are made up of all these components, and you need to match them codimension 1 to codimension 1. That's the face, that's the outside hull. But that still doesn't get you very far away from the origin to build them up piecemeal like that.
What Tony's really saying here is that it's all well and good understanding the unit cells, but it's the spacing of the hyperplanes in the multigrid that actually identifies and determines what the tessellation looks like.
Exactly.
That will determine what the ordinal indices of the component of that multigrid look like, which tells you where. And if you think about the De Bruijn thing, his pentagrid, the various intersections told you what shape of tile to use and in what orientation. And that's exactly the same thing that you get with a multigrid in n dimensions. So with it, you can't understand the tessellation from the unit cells alone. You have to have a corresponding multigrid. The two things go hand in hand.
So you have to go back to the full star if you're working with the in the three-dimensional quasicrystal star, where you have 6 elements, and you're working with 3 of them at a time. You need to, in order to place it in space, you need to reference all 6 of them, and that's what Andrew was proving. Really impressive work. Really, I never thought we'd get this far.
Well, that sounds like a hopeful note to end on. Thanks again, Andy, for nice, interesting talk. So, yeah.
Thank you.
Next week, I think Lou is talking. Is this correct?
I think so.
Right. Okay. We don't know what he's talking about, but he does.
Yes, I'm trying to remember what it was we were going to have me talk about.
Okay. Well, we have a whole week to think.
I'll have to send you an announcement.
Yeah. Okay.
By the way, I put into the chat line a clip about quasicrystals and the Riemann hypothesis from the N category cafe.
Oh, okay. So that's the homework for next week, is to prove the Riemann hypothesis.
Oh yes, Kaufman just you might as well. It's time. I just remembered what I'm talking about next week. I'm talking about the beginnings of virtual 3 manifolds. So I'm going to tell you about virtual Kirby calculus.
Okay.
Then AG will follow with making it more real 3 manifolds that can be whose quantum invariance can be calculated using virtual Kirby calculus. And then Heather will talk a little later on about the details of the calculations.
Great. Okay.
And I will send you my slides.
Yeah. Oh yeah, thanks, Andy. Yeah.
Fantastic.
Andy, you're
talk.
going to send Roger the slides.
I'll send them to you and to Roger, so you both.
Great. Thank you.
Okay, so see you all next week, folks. Bye now.